Hey, everybody. Welcome to this episode of Curley's Couch, which is actually Curley's carpet because my wife is teaching in the other room. Today, we've got a question that is one of my favorites because it's so comprehensive. It puts together so many of the skills that we've learned this year and makes us use our skills in different ways. All right. So, question one, a spring with a spring constant of 30 newtons per meter. Okay, so there's our spring constant, little k, 30 newtons per meter, is compressed 20 centimeters. Okay, so that's our compression, which is the x. Remember, 20 centimeters we have to convert into meters. Okay, so there's 100 centimeters in every meter, so we got to move the decimal place over two places, so it's 0.2 meters. Is used to launch a 50-gram toy box of cats. Okay. That's a Mr. Christensen special for you. 50-gram toy box of cats. So since it's 50 grams, we have to convert that into kilograms. So we have to move the decimal place over three spaces. So that gives us 0.05 kilograms up a ramp that is 30 degrees. And it gets to a height of 50 centimeters, which we converted to 0.5 meters. Above the position, it leaves the spring before it slides back down. Assume there is friction. Okay, so determine the amount of energy lost due to friction, and that's implying on the way up to the maximum point. So if we're looking at energy accounts, this will be A right here, okay, and this will be B when it gets to its maximum height. So for A, for the first part of our LOL, there's no EK because it's not moving. There's no EG because that's a height of 0. Okay. And there is ES because it's loaded on a spring with a spring constant of 30 newtons per meter. Okay. So we're going to put all of our energy, and we'll just make it 3 boxes. We'll quantify it in a second. Okay. So the only thing that we've got for A is going to be our EG. Okay. What's in our system? We've got our spring, we've got the earth, we've got our box of cats, and we've got the track. Okay. On the second part, when it gets to its maximum height, once it hits its maximum height as it's sliding up, it stops. So there's no EK. Okay. There's obviously going to be a height because it's at its maximum height, so we are going to have EG. The spring is no longer impacting the movement, so we're not going to have ES. And it told us that they're assumed friction, so there is ETH. Okay, so this EG is going to equal, oops, this is ES on this side, my bad, equals EG plus ETH. Okay, so all of that energy that's stored in the spring ends up going to our gravitational potential energy account and our thermal energy account. Okay, so it wants to determine the amount of energy lost due to friction. So it wants us to find what this ETH is. So in order to find ETH, we've got to find the other two variables. So first, let's do our ES. So our ES equation is 1/2 of the spring constant multiplied by the compression squared. Okay, so if we wanted to calculate ES equals 1/2 of our spring constant, which is 30 newtons per meter, okay, multiplied by the compression, which is 0.2 meters squared. Okay, so let's calculate that. So we got 0.2 squared multiplied by 15 because we can combine those two terms, and it equals 0.6. So 0.6, and our unit is Mr. Christensen's dog's name, which is joules. Okay, so 0.6 joules equals, you can see that, yeah, equals EG plus ETH. We'll come over here. We'll use this real estate over here. So we'll calculate EG now. So our EG equals our mass times our gravitational field strength multiplied by our height. Okay? So our Eg is going to be our mass, which is 0.05 kg, multiplied by 9.8 newtons per kilogram, because that's the gravitational field strength of Earth, multiplied by our height, which is 0.5 meters. So let's do that. 0.05 multiplied by 9.8 multiplied by 0.5 equals 0.245 joules. So our Eg equals 0.245 joules. So what we've got for our equation for our first part where it's loaded to our maximum when it's at its greatest height is, so ES equals EG plus ETH. Our ES is 0.6 joules equals 0.245 joules plus ETH. So this is just some simple algebra. We'll move this over here. So it'll be 0.6 joules minus 0.245 joules equals ETH. Okay, do a little math magic here, and that is going to be 0.355 joules equals ETH. Kaboom, boom shakalaka. That is the energy lost that goes into or due to friction. Okay. So now for our bonus question, this is where the fun begins. Determine the coefficient of friction between the box and the ramp. So let's see. I'm just going to tilt this down here for the bonus. Hopefully this works. Hopefully you guys can see that. Okay, so determine the coefficient of friction between the box and the ramp. So we're going to have to use what we have for ETH. Okay, so our ETH equals FFK multiplied by the distance. Okay, we know ETH from our first problem, which is 0.355 joules. And FFK, the way we find that is it's going to be our coefficient of kinetic friction, which is what we need to find, okay, multiplied by the force normal, okay, multiplied by the distance covered. Okay, so we've got to find two things in order to find this. We only have one thing right now, and that is our thermal energy. So let's find force normal first. In order to find force normal, we've got to go back to our trusty force diagrams. Okay, I'm gonna lay down. That's gonna make this easy. So hopefully my hat doesn't get in the way. Okay, so this right here is going to be, I'm going to put it down here so it doesn't get in the way of my components. Force of gravity. Our force normal is perpendicular to the surface. So that means we're going to have, I'm sorry, these angles aren't perfect. It's hard for me to draw down here. Our force gravity components. So this will be FGX. This will be FGY. And since the box is moving up the ramp, this is one of those goofy scenarios where we've got two forces or components going in the same direction. So our force friction, instead of going up the ramp, it's going to be going down the ramp, resisting the direction of intended motion. Okay? So we're looking for force normal. Okay? And since we know that the box o' cats is moving parallel to the surface, it won't be accelerating perpendicular because the box of cats isn't blasting off into the wild blue yonder, okay, perpendicular to the surface, nor is it tunneling at an angle of 30 degrees down into the earth. So we know that those forces or components need to be balanced. So what we'll do is we'll do a sum of forces in the y direction equals Fn minus Fgy equals 0, which means that these two things have got to be equal. Okay. So let's do a little bit of math. First, we got to find our FG. This one's simple. So we just take our mass, which was 0.05 kg, multiplied by our gravitational field strength per kilogram. So we got to do 0.05 multiplied by 0.98. Multiplied by, or 9.8. All right, 0.49 newtons. Okay, so our FG equals 0.49 newtons. Okay, so that's our hypotenuse. Okay, and what we've got to do is we've got to find FGY, which is adjacent to our 30-degree angle. Okay, so what that's going to look like is that's going to be cosine 30, okay, equals our opposite or our adjacent, sorry, a little brain fart, over our hypotenuse. So our hypotenuse is 0.49. Okay, 0.49 newtons. And our adjacent is what we're looking for, which is FGY. Okay, so we take cosine 30 and multiply it by 0.49. Cosine 30 times 0.49 equals FGY. So let's do that. Cosine 30 multiplied by 0.49 0.423. Okay, let's call it 0.423 newtons. Okay, so that's our force normal and our FGY. So we know this part. So we've got 0.355 joules equals mu k, so our coefficient of kinetic friction, multiplied by 0.423 newtons, multiplied by the distance. So now we've got to find the distance. And this seems scary because you got to determine how far it goes up the ramp. Okay. But really, you're just going to be using your same trig skills to figure that out. Because look, I'm just going to redraw the ramp down here. We've got our ramp. This is 30 degrees. Okay. We've got a height of, it's 0.5 meters. Okay. And we've got to determine this piece, how high it goes up. So we have our opposite. Okay. So we've got 0.5 and we've got to solve for the hypotenuse. So it's going to be very similar to something that we've done. So in this case, we would use the trigonomic function sine because we have the opposite. Okay. So it's going to be sine 30 equals 0.5 meters because that's the opposite over the hypotenuse, which is our distance. Okay. Does that make sense? You can't really answer me, but that's a rhetorical question. So sine 30, move the d over, multiplied by d equals 0.5 meters. Okay. Divide this 0.5 by sine 30. Okay. Get rid of that. So 0.5 divided by sine 30. That gives us 1. How convenient. 1 meter. So this distance right here is 1 meter. Okay, so we're going to take all of this, okay, to solve for this guy right here. So we've got 0.355 joules, which was our ETH. Okay. That equals our mu k, which is what we're looking for, our coefficient of kinetic friction, multiplied by our force normal, which was up here, which we got 4.23, or 0.423, 0.423 newtons, okay, multiplied by our distance, which is 1, okay, to get mu k. So this, obviously multiplied by 1, it's going to be the same thing. So we're going to take this, divide it by 0.423. That's going to give us our coefficient of kinetic friction. So 0.355 divided by 4, 2, 3 equals 0.839. 0.839. There's no unit because it's a coefficient. So our coefficient of kinetic friction is 0.839, which is pretty substantial. A lot of friction going on there. So if we were to come back up here to our LOL chart, okay, there we go. ETH is probably going to be pretty substantial, okay? It's going to be bigger, so it'll be 0.355 is ETH compared to 0.245. So our ETH is going to be a little bit bigger, right? There's a bunch of friction going on. 0.839 is a large coefficient. I know that's a lot of steps. It's a lot of funk. But yeah, it's a fun question. Since you guys are only getting one question a day, there's a lot of things to put together. If you still have questions about this, okay, and you want to work it out, get in contact with me or Mr. Christensen. This episode of Curley's Carpet was brought to you by the Wheat-Warrenville South Ornithology Club. Hope you guys are staying safe. Your family's, staying healthy and all that good stuff. All right, we'll see you guys later.